Thank you for the introduction, and thank you to the organizers for inviting me to be here today. I've already been having a lovely time going to several of the talks this afternoon. You know, one thing, undergraduate research has changed a lot since I was an undergraduate. You know, I mean, even just in the past decade and a half, it went from a thing that only a few people were doing in a few places to now, you know, really significant part of the path, you know, through the mathematics major to math graduate school, and we have, you know, great things for undergraduates doing math research like this conference. So it is exciting to be here and be a little part of this weekend conference. All right, so I'm going to talk to you about the chemistry of primes. I heard some people when they were coming in talking about whether there would be any chemistry in this talk, and there actually will not be any chemistry, so some of you may be disappointed, some of you pleased. That it is what it is. There will be no chemistry, just primes. All right, so the primes. The primes, as you know, are the basic building blocks of the integers. And what do I mean by that? Just in the simple sense that you all know that every integer can be written as a product of primes, but primes are indivisible. They can't be written as a non-trivial product. That's what makes a prime, right? So here are the first several primes, 2, 3, 5, 7, etc. And numbers that are not prime, like 4, we can write as the product of primes. 6 is a product of primes. 8, 9, etc. The other numbers are product of primes. But what makes prime numbers prime is that they're indivisible. However, I'm going to turn that all on its head, and I'm going to consider what happens when we work with systems of numbers that are larger than the integers. So I'll call these extensions of the integers. And then some strange things can happen with the primes. So here's the first extension of the integers I'm going to consider. So it's the set of the numbers a plus b times root 2, where a and b are integers. So that collection of numbers, it includes the integers, because in this expression I always take b to be 0. I get all the integers. I get all the integers, and I get the square root of 2, and I get 7 times the square root of 2, and I get 3 minus 4 times the square root of 2. I get a bunch of other numbers. And so in this extension, which of course, if you know this terminology, is a ring. It's the ring we'd call z adjoining the square root of 2. But if not, you can just think of these numbers here, which include the integers, but a little bit more. Now some things happen. So the first thing, which is not so surprising, is 2, which was supposed to be prime, a prime number, indivisible. It's now factors. It's a square, the square root of 2 times the square root of 2. Okay, well that seems like, well, you throw in the square root of 2. Okay, that's going to happen. But in fact, more subtle things happen. For example, 7, which in the integers was a prime number, 7 now factors as 3 plus root 2 times 3 minus root 2. You can all check that quickly in your head, I'm sure. So 7 no longer indivisible. 17 here is 5 plus 2 root 2 times 5 minus 2 root 2, also factors. So now our primes start factoring, but not all of them. 3, 5, 11, and 13 remain prime, remain indivisible. So some of our primes factored are no longer primes, but some of them remain prime. All right, so here's my picture, my chemistry picture. So I've lined up a bunch of beakers here with the various primes in them. So this has 2 in it. This has 3 and 5 and 7 and 11. And this row of beakers goes on. It's an infinite row of beakers, all the primes there. And I imagine I've got this solution, this a plus b root 2 solution, and when I pour it in to the first beaker, those 2's, they break up. And now that beaker that used to be full of 2's is now full of root 2's. But nothing will happen with the 3's. They'll stay as they are, and the 5's. And now, in these 7s, they break into 2 different pieces. So here too, it broke into just 2 copies of the same piece. I've just got root 2's. And here now I've got 2 different pieces. I've got 3 plus root 2 and 3 minus root 2. Those are 2 different kinds of pieces. So now where I used to have just one kind of thing, 7s, now I have 2 different things here. And nothing happens with 11s. And I imagine I go on and on and on through all the so-called primes, the primes and the integers, and see what happens whether they're still prime. Okay, so you could do this not just with, say, throwing in the square root of 2 into your mix. Here's another similar extension where instead of the square root of 2, I put in the square root of 3. And now, some numbers like 2 here, factors, root 3 plus 1 times root 3 minus 1, and 3, of course, factors. That was the obvious one. And here 11 factors and 13 factors, but 5, 7, and 17 remain prime. So for any of these examples, you could go through and kind of individually see what happens, which primes stay prime, which primes factor and split up. And I'm going to introduce the terminology that we use in number theory to describe this. So we would say that a prime splits if it breaks into distinct pieces in an extension, such as 2 and 11 and 13 here. And a prime ramifies if it breaks into pieces, some of which are the same, such as 3 here. It factored into 2 factors that are the same, and so that's called ramification. A prime ramifies when that happens. And then we say a prime is inert if it remains prime in the extension. So here 5, 7, and 17 are inert. All right, and that is actually the word that we use, which kind of inspired me to think of this as the sort of chemistry of reactions with the primes. All right, so those are our 3 words to talk about what can happen. It can split into all distinct pieces. It can split into pieces, some of which are in common. We call that ramifies, or it's inert. And once that we see that this is happening, there are many questions we might ask about this behavior. We've seen a lot of primes splitting into 2 pieces. You might want to know, well, how many pieces could a prime split into? And then also, especially as we imagine this infinite row of beakers, or all the primes lined up, you might ask, given some fixed extension, how often do primes split? Do most of them factor? Do most of them stay inert? Do most of them stay prime? What's the typical behavior? So given a fixed extension, what proportion of the primes split? What proportion are inert? Okay, and here's the same question. I'm going to just phrase it in a different way because I like the probabilistic language, which is given a fixed extension and a random prime, what's the probability that that prime splits or that it's inert? So all I really mean by that is the same thing, by probability I just mean what proportion. But one reason I like this probabilistic language is it allows us to ask the following question, which takes a little bit to wrap your head around, which is, are these probabilities for one extension independent of the probabilities for another extension, or are there correlations between splitting behaviors in 2 extensions? So what that means is maybe you have 2 different extensions, and what this question asks is if you know something splits in one extension, does that give you information about the likelihood that it splits in another extension? Does that make it more likely or less likely? I mean, you might just want to wonder in general, are there primes that are more likely to split, or are there extensions that are somehow buddies in such a way that splitting in one extension tells you a lot about splitting in another extension? So that's what that independence question is about. Okay, so those questions were just phrased in casual language. To do mathematics, we have to make those questions precise. Okay, so I have to tell you something about what I mean by these extensions, extension of the integers. So here's a definition. So given a polynomial with integer coefficients, so it's actually a monic polynomial here in the variable x, and these a sub i's are all integers. So we've got a monic polynomial with integer coefficients. Here's how I'm going to make an extension of the integers. I'm going to start with the integers, And then I'm also going to include all of the roots of the polynomial. And then I'm going to include in what I'm going to eventually call the extension all the numbers I can get from adding and multiplying integers and roots of this polynomial. So that's what I'm going to mean as an extension of the integer, something I can build in this way. It's always built out of a single monic integer coefficient polynomial, and the way that I extend the integers is by putting in the roots of this polynomial, and then I have to, because I actually want a place where multiplication makes sense and I need addition, I have to put in all the other numbers I can get by adding and multiplying. So that's so that I actually get what we would call a ring in abstract algebra, which is a place where you can add and multiply. It's a good place to be doing things like factoring. All right, so that's what I mean by an extension of the integers. So for example, before I gave what I said was an extension of the integers, and now I'm going to make sure it's consistent with this definition. If we use the polynomial x squared minus 3, then the roots are root 3 and minus root 3, and then this set of numbers, a plus b root 3, where a and b are integers, are exactly the set of numbers you get by taking the integers, those two roots, plus and minus 3, and everything you can get by adding and multiplying those things together. Okay? So the extensions that we saw in these examples are quadratic, in the sense that the polynomial they come from is quadratic. In general, what I've defined here it would be a degree n extension. As you may know, once the degree of this polynomial is 5 or greater, it's not so easy to write down the roots. In fact, for some of those polynomials, you can't write the roots in terms of root symbols, square root and nth root symbols, but yet they still are some numbers. Whatever they are, we can just say, okay, they are what they are, even if we can't write them down, and I can still abstractly have an extension coming from even very high degree polynomials. Any questions? Okay. So that's what the extensions are. And then I have to tell you this probability language. I have to make sense of it. So I want a probability that a random prime has a certain splitting behavior. And so the trouble is, it's a little awkward to talk about a random prime. In particular, it's awkward to talk about a random element of a countable infinite set. All right, so how am I gonna do that? Well, if I weren't interested in all the primes, but simply the primes up to some large number n, if I only cared about the primes up to some big n, then that probability would be easy to define. It would just be the number of primes up to n with whatever property I'm interested in divided by the total number of primes up to n. So that would be fine if I only care about primes up to n, but I care about all the primes, and so the trick to making this definition is that I take the limit as n goes to infinity of this expression. All right? So that somehow captures all the primes, because even at any particular time I'm only seeing primes up to n. Since I make n bigger and bigger and bigger, eventually I'm seeing all of the primes. Now I love this limit because one thing about this limit is technically I should say the probability is defined to be this expression if the limit exists. It is totally not clear that such a limit exists. And for most of our life, when we start writing down like limits, like when we learn them in calculus and so forth, whenever you write down a limit, either it's obvious it exists or it's obvious it doesn't, because you've done something like make some jump discontinuity. And this is a limit that's totally not clear whether it should exist or does exist, how you would prove it, if you should expect it exists or sometimes doesn't. But anyway, this probability is defined to be this limit if indeed it does exist. So if you want to say something about it, part of that will have to be proving the existence of this limit. All right. So now I've made the notions that we need for these questions precise, and I'm going to tell you some answers. So here's one kind of answer. So given a fixed extension of the integers and a random prime, the probabilities of the various splitting behaviors were determined and proven, not in this same language, but essentially the same facts quite a long time ago by theorems of Gauss in 1796 and Dirichlet in 1837 in the quadratic case. So that's the case that we saw in the two examples with the square root of 2 and square root of 3, where the polynomial that we build our extension from is degree 2. And by Frobenius in 1880 in the general case. So in the degree n polynomial case, when you can't even write down the roots, but they still are something, whatever they are, Frobenius understood the probabilities of various splitting behaviors as long ago as 1880. And so here's the quadratic, I'll give you the quadratic theorem since those are the examples we've seen. And so it follows from Gauss's theorem of quadratic reciprocity and Dirichlet's theorem on primes and arithmetic progressions. So these are two of the big classical number theory theorems you're going to learn if you, take some number theory courses. Quadratic reciprocity being a statement about whether A is a square mod B and relating that to whether B is a square mod A, which is a really big surprise that there should be such a relationship. And Dirichlet's theorem on primes and arithmetic progressions telling you that if you have an arithmetic progression which doesn't obviously preclude primes because, for example, all the numbers in it are divisible by 7, then in fact it has primes and infinitely many primes, and one can say about how often. So if you combine those two sort of really fundamental theorems in number theory, you can conclude that given a fixed quadratic extension and a random prime, that there's a 50% probability that the prime from the integers splits, and in which case it splits into two primes. Oh, and there's a 50% probability that it is inert, that it doesn't split, and then there's a 0% probability that the prime ramifies. So even though some primes do ramify, it is a probability 0 event. So let's just go back to this example. In our extension a plus b root 2, where a and b are integers, we saw this one prime ramify and a few split and a few inert. So that's, we didn't take big N very high, and our limit is n goes to infinity, but it seems to be somewhat consistent. In particular, 2 is the only ramified prime in this extension. And so now you can see that it's probability 0. So remember, the definition was we go up all the primes up to some big N, and then we take the probability up to that big N, and then we take the limit as n goes to infinity. So there's only going to ever be as big as n gets, since 2 is the only prime that ramifies. The numerator's only ever 1, and the denominator is the number of primes less than n, which of course gets bigger and bigger. And so we have, in fact, in this case, even proven that this limit exists, indeed, and it is 0. All right. So those are some first kind of answers to that question of how often do things happen. So splitting and inertia are the typical behaviors that each happen about half the time, and ramification is a feature that's so rare that it's 0% of the time. All right, so let me tell you about some of the methods that go into this. Really, these classical theorems that I said could be combined to get this statement. So geometry of numbers, counting lattice points in regions, that's what geometry of numbers means. You think, well, what does counting lattice points in regions have anything to do with what we were just talking about? Well, here's an example. We didn't talk about this, but instead of a plus b times root 3, if I took a plus b times the square root of minus 3, then those are complex numbers, and they naturally make a sort of nice lattice in the complex plane. And so that's sort of where there are lattice points. And even when you have a plus b root 3, it turns out you can make it a lattice in a different two-dimensional space. If you squish it down in the reals, it doesn't look like a lattice. It's just all squished down. But if you look in the right two-dimensional space, even a plus b times root 3 is a lattice. And so this comes down to questions of counting lattice points. And so here's a lattice. This is a slightly different lattice. This is like when you, instead of root minus 3, you have 1 plus root minus 3 all over 2 that you add on, and you get a lattice like this. And so these blue and green shapes are regions. And so the geometry of numbers is about having regions and wanting to know how many lattice points there are in them. And usually, the sort of the first approximation is that if you know kind of how big, how spaced out the lattice is, and you know the volume or the area here in this two-dimensional case of your region, then that should tell you approximately how many points should be in your region. Especially if the region is a nice big blob like this, up to some sort of smaller error, to first approximation, the number of points in the region will be the volume of the region sort of divided by the spacing of the lattice. However, this green region here is to show you that geometry of numbers is a subtle area, because as you see here, I can make a green rectangle that gets longer and longer and longer and has more and more and more volume or area in this case, but never picks up a lattice point. So that's what makes it, a whole area, in fact, currently even an active area of mathematical research to try to understand what you need to know about a region to make sure that its volume gives you a good approximation for the number of lattice points. So that's one of the big inputs especially into Dirichlet's theorem. Okay. All right. Oh, this is just what I was saying in words here. Often, but not always, the number of lattice points is approximately given by the volume, but the whole meat of the work is what hypotheses do you need to actually make that work. All right. And another big tool that goes into proving particularly Dirichlet's theorem is complex analysis. Okay, here I'm talking about primes factoring. Where does complex analysis come in? Well, let me tell you. So we wanted to understand, as you go through the primes, about what proportion of them split. Okay? And it turns out that a handy kind of thing to consider to answer that sort of question is this sum here, where I sum over the primes that split, I sum their reciprocals. So maybe in one extension, 7 and 17, they were the first few primes that split. So the point is, this is an infinite sum, and how that infinite sum grows is related to the proportion of p that split. All right, somehow the more p that split, the more terms there are in that sum, and the more sort of small, smaller denominators you have, and so larger numbers, and so the way that one uses complex analysis, let's just say the way that one uses analysis to understand the portion of p that split is through understanding this sum. So here are some examples of other sequences of numbers where we sum their reciprocals. So, right, as you probably know, if you sum the reciprocals of the integers, that does go to infinity. So that grows and grows. But if you say, for example, just sum the reciprocals of the primes, that goes to infinity more slowly in a way that can be actually made precise. That has to do with the fact that the primes are not dense in the integers. If you go up to about x in the integers, the prime number theorem tells you that you only see about x over log x primes. But still that's pretty close to x, so that does go to infinity. Whereas if we took another series here, say the reciprocals of the powers of 2, that doesn't even go to infinity. It goes to 1. So it tells you there are a lot fewer powers of 2 than there are primes. And so the way the analysis comes in is understanding this proportion through understanding the rate at which this sum grows. In particular, in this case, it'll go off to infinity, and you want to understand exactly how fast is it going to infinity. And then the thing that I think is somewhat mysterious is, of course, that was all an explanation of why you might want to use some kind of real analysis to understand this question. But I actually said it's complex analysis. And that has to do with the fact that analysis is just much nicer in the complex numbers than the real numbers. So even when you have some questions like this, or even this, basically what this is getting at, a more basic question like what does the number of primes up to x look like, it turns out that it's much easier to understand that using complex analytic techniques than real analytic techniques, just because the complex numbers are a nicer place to do analysis, even if you only care about real numbers. All right. So yeah, so that's why the analysis is complex. Not really because the roots of our polynomials could have been complex. That is a totally different orthogonal appearance of the complex numbers than the fact that they appear in this analysis. So any questions? All right. Yes, so even though only real numbers are involved, the complex numbers are great. So now I told you about how often one thing happens and how often another thing happens. And now I'm going to get back to this question of independence. All right, and now we're going to see kind of an example that's going to make a little more sense what's going on. So in fact, there's a beautiful a theorem that tells you exactly when independence happens, and that is that the splitting behaviors for probabilities for two extensions, let's call them R and S, are independent exactly if R and S have nothing in common. All right? And the way, mathematically, what that means is that R and S intersect only in the integers. So for example, the first two extensions we saw were when we throw in the square root of 2 and you throw in the square root of 3. And those have nothing in common except the integers. And so what that means with this result here is that if I tell you a prime splits in, when you throw in the square root of 2, that gives you no information about whether it's more or less likely to split when you throw in the square root of 3. And those two extensions have nothing in common. But here's another example. So these are quartic extensions, so they can actually be generated by roots of a single quartic polynomial. I will leave that as an exercise for you to see if you can find such a quartic polynomial. But indeed they are. So here R is going to be an extension which the numbers in it are all of the form A plus B root 2 plus C root 3 plus D root 6, where A, B, C, and D are integers. All right, and similarly, S is a similar thing, except instead of root 3 and root 6, I have root 5 and root 10. Okay, so each of these are quartic extensions. They can be generated by a quartic polynomial. And here, R intersect S is our very first extension we saw, the numbers of the form A plus B root 2, where A and B are integers. So these two extensions have something in common. So you might even naturally guess that that if something splits in R, maybe it's more likely than, that gives you information, it's more likely to split in S because maybe it had something to do with the root 2. All right, so let me just say that, if a prime splits already here, when you throw in the square root of 2, then of course it can't be inert in either R or S. And if a prime is inert here, if when you throw in the square root of 2, it's inert, it doesn't factor at all, then it's somehow you've already tried the square root of 2. That didn't help you break it down. It's more likely than a prime with no information about it to be inert in both R and S. And so this leads to a correlation between splitting behaviors in R and splitting behaviors in S. It means that information about whether a prime split in R tells you something about whether it's split in S, and vice versa. And that, I think, really makes sense. I mean, this is a nice a nice kind of theorem. It's like, oh, that's what we would want to be the case. We'd want it to be the case. Well, of course, if the extensions have extra numbers in common, there should be some correlation, and if they don't, then there's no correlation and everything's perfectly independent. So that is a really clean kind of result, the kind you'd hope for. All right. So now I'm going to review the questions that I just talked about that are very classical questions in number theory, and then get to a new question. So I asked, given a fixed extension and a random prime, what's the probability that that prime splits or that it's inert? And we saw the answer in the quadratic case, and I told you it was known in the general. I didn't write it down. And then we asked, are these probabilities for one extension independent of the probabilities for another extension or their correlations? And I gave you the complete answer to that in arbitrary degree extensions. It's this beautiful answer. There's exactly correlations when the extensions themselves have something in common. All right. So now there's going to be a slight twist, and we're going to ask a different question, which is, given a fixed prime and a random extension, what is the probability that the prime splits or that it's inert? And if you're, only 99% listening and not 100% listening, then that sounds like exactly the same question. But it's not the same question, and I try to color code this here. So before we were asking about a fixed extension, like we only care about one extension, or maybe if we're talking about independence, 2 extensions at a time, and all the primes, a random prime among all the primes. And now, the random thing here is in red. It is switched from being a random prime to a random extension. So we have a fixed prime. Maybe my favorite prime is 7. Maybe your favorite prime is 3. We care about, our fixed primes, and we care about all the extensions in the world. We're concerned about all the different ways of adding on to the integers to get bigger systems of numbers. And we want to know what is the probability that, the prime, say 7. I really like 7. I want to know in all the extensions out there, like what does 7 look like? That it splits or that it's inert. And then we can ask, are these probabilities for one prime independent of the probabilities for another prime, or their correlations between the splitting behaviors? So if my favorite prime is 7 and yours is 3, and I take some random extension and I find out that my prime 7 splits, does that give you information about how likely your prime 3 is to split in that extension? Does 7 and 3 have some kind of something in common? All right, this is supposed to be the analogy of extensions having something in common, but it's a little harder to see what it would be. Okay, so here's the picture now. With our infinite line of beakers, I line up all the infinitely many extensions. I mean, it turns out it's a countably infinite list, just like the list of primes. So I line them up in this very long countably infinite row. I've got all the different extensions here, a plus b, root minus 3, a plus b, root minus 1, root 5, root minus 7, etc. And I've got all of them in here. Even when I can't write the numbers with roots, they're still there. And I take my favorite prime, which of course I've been saying is 7, and I go along and see that, in this first extension 7 splits. In the next extension it's inert, then it ramifies, then it splits. So how does 7 do in all these different extensions? Okay, so this is really a different question. And if you don't care about primes or extensions of the integers, then it just sounds like, same old, same old. But if you actually cared about these objects and you wanted to use these results for something, which, eventually we will to apply them to other questions, then you really need to know one particular question or the other, and they're not the same. So here's a very down-to-earth kind of analogy. Suppose that you wanted to grow some tomatoes without pesticides. So here, my analogy to the different extensions on sort of the one axis and the primes on the other are going to be different varieties of tomatoes and different pests that might affect your tomatoes. So you consider several pests in your area. Maybe the pests are like primes, and types of tomatoes that are like extensions. And you find that each pest kills about 1/3 of the types of tomatoes. Okay? So, you maybe read this in a study. Okay, each of these pests kills about 1/3 of the types of the tomatoes. So does that mean you just have to give up and be like, okay, I'm going to plant some tomatoes, about 1/3 of them are going to die? No, if you're going to plant the tomatoes, then you want to know, what about each type of tomato? Maybe this is happening because some types of tomatoes are really, resistant to pests, and some types are getting eaten by all the pests. In fact, if you want to pick out types of tomatoes, this first kind of result is pretty useless to you, because you're not picking types of pests. That you're picking a type of tomato, to be able to pick a type of tomato and then consider all the possible pests that might get it. So anyway, just give this example to sort of illustrate that these are really different questions, and if you're planning to use this piece of mathematics to apply it to some situation, they're really useful in different circumstances. They're not sort of approximately the same question, even though you can phrase them with the same words in a slightly different order. All right. Okay, so what are some first guesses? What might you guess the answers would be? So these are these questions given a fixed prime and a random extension. So my prime 7, I look at all the extensions. What's the probability that it splits or inert? And then would they be independent, for my favorite prime and your favorite prime? So unlike extensions, where you could actually say like, oh, two extensions have something in common if they shared literal numbers in common besides the integers, which they all had to have. How do you even guess like which primes would have something in common? Should 7 and 3 kind of be in the same plan, but 5 and 13, or no, who knows? And so, as we usually do in mathematics, if we can't think of any reason why something should be one way or the other, we might just sort of make the default guess. And so the conjecture, and what I think basically everyone expected, is that all the primes should be independent. There should not be any kind of correlations between different primes. That if you take a random extension and you get some information about how some primes split, that should not tell you anything, any biases about whether any other primes would split or not. That's the natural guess and what people expected, and the conjecture that was made. And to talk about what the truth is, we have to make the new question precise, which isn't going to be too difficult. We already made the old question precise, and this is, of course, a similar kind of question. So remember, this is the old question. When we had a fixed extension and a random prime, we just had a fixed extension, whatever it was, and then we took this limit as n goes to infinity of the proportion of primes up to n with whatever splitting behavior, whatever property we were asking about. Okay, so now I have some fixed prime, like maybe my prime is 7, and I want to know in a random extension what's the probability that it has a certain splitting behavior. And I want to define it to be, okay, same kind of machine, right? I'm going to take the limit as n goes to infinity. And then now there becomes something a little funny. And it actually goes back to that slide I had where I line up the beakers. When I lined up the primes, 2, 3, 5, 7, everybody knew how that list continued on, right? How I was lining up the primes. I'm lining them up in order. There's only one order you could be talking about. But now when I have these extensions, each of them comes from this polynomial. The polynomial has lots of coefficients. The extension has numbers in it. If you want to line them up, if you want to set them out in some order, then you have to have some way of ordering them, some invariant of extensions that kind of measures how far out it should be in the list. So it needs to have some kind of invariant here so that we can take extensions with that up to n, and then the limit as n goes to infinity. And so one notion you can put here is something that's called the discriminant. So I'll say something about the discriminant, which is the discriminant is an integer valued function of extensions. So for example, if you build an extension from a quadratic polynomial, like we have in our first couple of examples, then the discriminant of the extension is very closely related to the discriminant b squared minus 4c that's used to solve the quadratic equation. All right, so the discriminant in that sense. Now it turns out that even degree n polynomials have a notion of a discriminant, one number you can attach to them, and that's very related to the discriminant of the extension, even though you can no longer use roots of that discriminant to solve the higher degree equations. So the discriminant is one, it's just some way to measure extensions. But here, unlike primes where you really couldn't argue, I've got my way of ordering the primes, you've got your way of ordering the primes. No, we all order the primes in the same way. We could replace discriminant with other functions here. If we replaced discriminant with another function here, then we get technically a different question. All right. We get what is technically a different question. So there's some other function, whatever it is, it's called the conductor. It's another integer function of extensions. And I'm just going to give you a chart here where I give you a bunch of polynomials, and then I'm going to give you the discriminant of the extension you get from using roots of that polynomial and the conductor. And I have conveniently factored the discriminant and the conductor for you. Otherwise, it would have just looked like a random list of numbers. Okay, so you can immediately notice that the discriminant and the conductor contain exactly the same prime factors if you're not looking at multiplicity. So that's in general true and important. And in fact, I'll just tell you here that these primes that appear in either the discriminant or the conductor, those turn out to be exactly the primes that ramify in the extension. Okay, so I said we're only finitely many. So like in the extension from this last polynomial, 5 and 17 are the only two that ramify. So these are very closely related numbers, the discriminant and the conductor. These have some more sort of powers in them. But they do actually order the extensions in a different way if you order them by discriminant or by conductor. The discriminant, it's easier to define. I didn't even tell you what the conductor was. But it has all these powers of primes that sort of seem to be kind of redundant. Is sort of a downside. And the conductor is much harder to define, but then it turns out to be simpler to work with once it's defined. And depending on the context or application, one ordering might be more natural. And so you should define like a discriminant probability and a conductor probability. And maybe you do one or maybe you do the other, but let me tell you that when this business started, everybody thought, okay, well, discriminant and conductor, they're basically the same. Yeah, the discriminant has some exponents in it, but they're basically the same. And so, yes, even though technically a priori these are different questions, of course we expect the answers to be the same, to not depend on how you line things up. Okay, so how do you go about solving a question like this? And this turns out to be much, much harder than the first question, where we had a single extension and we thought about all the primes. When you have a single prime and you think about all the extensions, it's much harder. And one reason is it's really hard to make a list of all the extensions. So I said that extensions are the things you build from these polynomials. So you might think it's not so hard to build a list of the polynomials, but it turns out what's really hard is to tell when two different polynomials give you the same extension. All right, so you can get all the extensions from polynomials, but then it's hard to know when you have the same one and how many times you have the same one. And so making a list that is really just a list of each extension occurring exactly one time is a rather difficult mathematical problem. And so one thing that turns out to be a good sort of simplification to make is to do something like fix the Galois group of the extension. So what that means is the symmetries of the extension. All right, so for example, when we threw in the square root of 2, if you turn all the square roots of 2's in those numbers a plus b root 2, if you turn all the root 2's into minus root 2's, it turns out that all the addition and multiplication works the same, so that makes it a symmetry of that extension. So if you fix a particular symmetry type, then that sort of gives you an end to tackle this kind of problem. In particular for abelian or commutative Galois groups, that means that when the symmetries apply, you apply one symmetry then the other. It's the same as applying first the other and then the first. It doesn't matter what order symmetries are applied in. Then you can use class field theory, which is one of the big achievements of algebraic number theory, to tell you what the possible extensions are. And then you can use complex analysis. We talked about kind of how that comes up before. For non-abelian Galois groups, so when the symmetry groups of the extensions are not non-abelian groups, the problem is actually open in general, even to essentially make a list of the extensions. But for some small groups, we can use methods from algebraic geometry to build an explicit space, a space whose points correspond to the extensions. So then you don't quite have a list, but you do somehow have a place that you can understand and write down where all the extensions live as points of some space. And so those are the methods that go into there. So now I'm going to give you an example kind of result. So this is a result of mine from now, I guess, quite a while ago, 2008. So it says given a fixed prime and a random extension. Oh my gosh, what was that? Okay, my clicker did something. There we go. So given a fixed prime and a random extension, so this actually turned out to be a big surprise. So I was a graduate student at the time, and my advisor was just sure I was wrong for quite some time, because no one thought this could be happening. It turns out that the answers that you get, the probabilities that you get of how likely things are to split, are actually different depending on whether you lined up those extensions by their discriminant or by their conductor. Even though everybody thought, discriminant, conductor, basically the same, there's just some powers in the discriminant. It turns out the probabilities are different. Okay, that's one thing, but that's sort of a qualitative thing. The numbers are different. A quantitative thing, the numbers are different. But even more surprising, a qualitative thing is different, which is that this question of independence, whether knowing 7 splits gives you some information about whether 3 splits in your random extension. So when you line up the extensions by conductor, the splitting probabilities are, at 2 different primes, are independent. But when you line them up by discriminant, there is not independence between the primes anymore. So it's not just like, I lined them up in different orders, and now, okay, my probabilities are slightly different because maybe I moved some forward and some back. But really, qualitatively, the behavior of things is different. That when choosing a random extension from kind of the first, big N extensions by conductor versus by discriminant, in one case you get primes behaving independently, and in the other case you don't. So that was, like as I said, a big surprise. And how you order the extensions really matters. It wasn't sort of just a technical point here. And here's my down to earth analogy. I mean, this makes it sound like less of a surprise, but which is, how you sort of line things up really is, even though it's all the same things in the end, when you're going up to N, it really is like, what kind of sample are you taking? And so it's like the question of, if you poll people in the US about their opinion on something versus polling likely voters, you not only can get quantitatively different results, like different, percentage of them prefer some candidate or have some opinion on an issue, but you can also get the qualitatively different results, like whether their opinion on the presidential race is independent of their socioeconomic status, right? That kind of independence question, right? That could be different for likely voters versus people in the US. I mean, that's very hard for maybe the general public to understand, but I think that in this room probably we can all understand that could be different sort of based on the sampling and this ordering the extensions, even though eventually you see all of them. The way that you take the limit as n goes to infinity, you see sort of certain ones first, and that really, like in this kind of sampling, affects the overall answers. All right, so to finish up, I just want to say, so these results were, I think personally, just interesting to know how often primes behave different ways in different extensions, but they also, because so many kinds of questions in number theory involve primes and factorization, have had a lot of applications in the years since 2008. So one application was by researchers to understand the complexity of factorization in extensions of the integers, sort of how hard the factorization problem can be. Also, these results were applied to help understand the number of solutions to polynomial equations. And here, all right, these are just two different polynomial equations, and you might want to ask about x and y that solve these equations. You might ask about x and y integers or rational numbers, or maybe integers modulo p for some prime. And it turns out that essentially because polynomials kind of come up as the key thing that make these kinds of extensions, that these results are useful to understand the number of solutions to polynomial equations. And also, these results were applied by researchers to understand length on highly curved hyperbolic surfaces. A couple of you know about hyperbolic surfaces because I came to your talks today and you were talking about hyperbolic surfaces. And it turns out that there are some deep connections between number theory and hyperbolic surfaces. That would be a whole nother talk. But because of those connections, these kind of results that I talked about on the last slide have been applied to better understand hyperbolic surfaces. All right, thank you.